In this lecture, we continue our discussion on displacement analysis of planar linkages by analytical method. Today, we start our discussion with an example. Let us look at this figure, which is the kinematic diagram of a 10-link mechanisms. This is the fixed link number 1, then O2A is the second link, ABC is this ternary link, link number 3, link number 4 is O4B, link number 5, link 6 is again a ternary link, link 7, link 8, link number 9 which is again a ternary link, and link number 10. So, we have 10 links, and let us look at the kinematic pairs. As we see, at this point O2, 3 links are connected, namely 1, 2 and 5. So, this is a second order hinge. Similarly, at O4, 3 links are connected, namely 1, 4 and 10. So, this is again a second order hinge. And finally, at C, 3 ternary links, namely 3, 6 and 9 are connected. So, this is again a second order hinge. Let us now calculate the degrees of freedom of this 10-link mechanism. We have already seen the total number of links n is 10. The number of kinematic pairs j is equal to, we have 7 simple hinges, namely at O, F, G, B, A, D and E. So, J1, that is 7, plus, as already mentioned, there are 3 second order hinges, one at O2, one at O4 and the other at C. So, 2 into 3, that is J is 13. So, the degree of freedom F is 3 times n minus 1 minus 2j, which is 3 into 9, 27, minus 2 into 13, 26, that is equal to 1. So, we see it is a single degree of freedom mechanism. That means, whenever any link moves, all other links move in a unique fashion. The question is, as this mechanism moves, let us see how does the point O, that is this point O, moves. To find that, we will use the links as link length vectors and try to find the vector O2O. Here, as we see, the vector O2O, we can write as vector O2D plus vector DE plus vector EO. One has to note that in this particular mechanism, O2ACD, this is a parallelogram. Similarly, O4BCG, that is also a parallelogram, and OECF, that is another parallelogram. That means, the link AC is same as the link O2D, link length EO is same as the link length CF, and so on. Not only that, the 3 ternary links, namely link number 3, 6 and 9, these consist of 3 similar triangles as indicated by these 3 angles, namely alpha, beta, gamma in each of these triangles. So, these 3 triangles ABC, CGF and CED are 3 similar triangles. So, now let me write the vector O2D as same as the vector AC, because they always remain parallel and of equal length, plus DE plus EO, which is same as CF, because CF and EO always remain parallel and of equal length. Now, the vector AC can be written as AC by AB into vector AB. That takes care of the magnitude of AC. However, the vector AC is at an angle alpha in the counterclockwise direction from the vector AB. So, I write e to the power I alpha. So, the first term vector AC can be represented as AC by AB into vector AB multiplied by e to the power I alpha. Now, the vector DE can be written as DE by DC into vector DC. That takes care of the magnitude of DE, but the vector DE is again at an angle alpha from the vector DC. So, we multiplied by e to the power I alpha. Then CF. CF I can write as CF by CG into vector CG. That takes care of the magnitude of CF, and again to take care of the direction I multiply by e to the power alpha. Now, as we see, because these three triangles are similar triangles, AC by AB is same as DE by DC, it is also same as CF by CG. So, all these three ratios are same. I can take any one of them, say AC by AB. That I can take common from all these three expressions. Same is true for e to the power I alpha. So, that also I take common. That leaves me with vector AB from the first term, then vector DC, which is same as the vector O2A, because DC is same length as O2A and they always remain parallel. So, here I write, instead of DC, I write same vector O2A. That leaves me with this vector CG, which is same as BC, because CG and BC are of equal length and they remain parallel. So, I write this as BC, which means the vector O2O finally comes out as AC by AB e to the power I alpha, and this summation of these three vectors, namely O2A plus AB plus BC, which is nothing but the vector O2O4. So, this vector O2O, which is vector O2O4 into AC by AB into e to the power I alpha. As the mechanism moves, all the vectors changes, but O2O4 never changes, because O2 is a fixed point, O4 is a fixed point. So, the vector O2O4 is always on our x-axis without changing its length. Neither the length AC or length AB changes, because those are the rigid link lengths. Same is true for this angle alpha, which is again the angle alpha of this ternary link. Consequently, as the linkage moves, the vector O2O never changes, which means the point O never moves in this mechanism. So, though this is a single degree freedom mechanism, all of the other points move as the mechanism moves, but the point O never moves. Just now we have seen that in the 10-link planar mechanisms with specific dimensions, there is one point which was not moving, though the overall mechanism had a single degree of freedom. Consequently, if we fix that point O, the point O which was not moving, let us fix it with the fixed link by putting a hinge, thus converting this hinge at O to a higher order hinge connecting three links, namely 1, 7 and 8. As a result, now we have an assembly of links where there are three 4-bar links, one 4-bar link consisting of 1, 2, 3 and 4 with the coupler point at C. There is a second 4-bar linkage consisting of link 1, 8, 9 and 10 with the same coupler point C, and the third 4-bar linkage consisting of link number 1, that is the fixed link, link 7, link 6 and link 5. Now all these 3 4-bar linkages had the same coupler point C, and this assembly moves in a unique fashion. In other words, it means there are 3 different 4-bar linkages which can generate the same coupler curve at the point C. As a result, this gives a wider choice to the designer to choose one of these 3 linkages to produce the same coupler curve. This is now what I will demonstrate with a model. Let us now look at the model of the 10th link mechanism which we have just discussed. There is a fixed link and there are 3 second order hinges all connected to the fixed link, which we marked previously as O2, O4 and O. There are 3 gray moving links, there are 3 red moving links and there are 3 blue moving links. We also note that this link length is equal to this link length and this link length is equal to this link length. Thus, this point O2, A, and this was C and this was D probably, these forms a parallelogram. Similarly, we have a parallelogram here and we have a parallelogram there. And these 3 ternary links, this red ternary link, the gray ternary link and the blue ternary links, they are similar triangles. That means this angle is equal to this angle is equal to this angle and this angle is equal to this angle. We have seen as a consequence of these special dimensions, these 10 link mechanisms move in a unique fashion because it has single degree of freedom. And this coupler point C can generate this coupler curve whether I use only this 4-bar linkage or this 4-bar linkage or this 4-bar linkage. All these 3 4-bar linkages generate the same coupler curve, and this gives the designer a wider choice to choose a particular one which may be convenient for the purpose. Now we shall discuss some useful results for 4-bar linkage which are most commonly used, and these results will be obtained analytically. For example, let us consider this 4-bar linkage, namely O2, A, B and O4. As shown in this diagram, at this configuration O2, A1, B1, O4, the 2 links O2, A1 and A1, B1 are collinear. Consequently, this link O4, B1 has taken one of its extreme position. It cannot go further to the left. As this link, the Crankrocker mechanism, this crank O2A rotates, there is another configuration when O2, A2 and A2, B2 again become collinear. And the corresponding configuration of O4B, that is this O4, B2, is the other extreme position of this follower link, that is link 4. So, we are considering a Crankrocker mechanism, and we see that as the follower goes from O4, B2 to O4, B1, during this movement, the crank rotates from O2, A2 to O2, A1. That is, it moves through an angle theta 2 star. During the return from B1 to B2, the crank rotates from A1 to A2. So, it rotates through an angle 2 pi minus theta 2 star. If the crank rotates at constant speed, then the time taken for the follower motion during the B2, B1 and B1, B2 are not same. Normally, we would like to have a quick return, that is returning from B1 to B2, it rotates through an angle 2 pi minus theta 2 star, and the forward motion, that is B2 to B1, it rotates through an angle theta 2 star, which is more than pi. The quick return ratio can be defined as theta 2 star divided by, we can write QRR, quick return ratio will be theta 2 star divided by 2 pi minus theta 2 star. Our objective is to determine the relationship between the various link lengths, namely the fixed length L1, the crank length L2, the coupler length L3 and the follower length L4, so that we can determine whether there is any quick return effect or not. Towards this end, we consider this figure which has been drawn for a mechanism without any quick return. One extreme position is O2, A1, B1, O4, and the other extreme position is O2, A2, B2, O4. During these extreme positions, the crank and the coupler are always collinear. This is the outer dead center, which is O2, A1, B1, and this is called the inner dead center when O2, A2 and A2, B2 are opposite to each other. The angle between them, once I can say 0 degree, in the other case it is 180 degree. So, for this configuration, as we see, the angle between O2, A1 and O2, A2 is pi. That means there is no quick return. It takes pi amount of rotation of the crank for the forward motion, and again another pi amount of rotation for the return motion. And this theta 4 star gives you the swing angle of the rocker. Let us now derive what is the relationship between various link lengths. If we consider the triangle O2, B1, O4, what we see, O2, O4 is of length L1 and O2, B2 is of length L2 plus L3 and O4, B1 is L4. And let us say this angle is, let me denote it by chi. So, considering the triangle O2, O4, B1, I can write L1 squared is L4 squared, sorry, let me write L4 squared is L1 squared plus L2 plus L3 whole squared minus twice L1 into L2 plus L3 cosine of the angle chi. Now, to determine the angle cosine chi, this value, let me drop a perpendicular from O4 to the line B1, B2. O2, B1, B2 is an isosceles triangle because this length O4, B1 is always equal to O4, B2. So, this perpendicular bisector meets B1, B2 at the midpoint. Now, let me call this point say D. We can easily see that B1, B2 is O2, B1 minus O2, B2. Now, link length O2, B1 is L2 plus L3. Minus O2, B2 is A2, B2 is L3 and O2, A2 is L2. So, this is L3 minus L2. So, we get 2 L2. So, B1, B2 is 2 L2. So, the half of that B2D will be L2. So, I can write B2D is L2. So, O2D, which is O2 B2 plus B2D, and O2 B2 is this. So, L3 minus L2 plus L2, which is L3. So, cosine of this angle chi is O2D divided by O2O4. So, cosine chi is L3, that is O2D, divided by O2O4, that is L1. So, we substitute this L3 by L1 here, and if we substitute this, we can easily show we will get L1 squared plus L2 squared will be same as L3 squared plus L4 squared. Thus, for a 4R linkage to have no quick return effect, that is, without any quick return effect, the link length of a 4R linkage must satisfy this relationship between its link lengths. L1 is the fixed link length, L2 is the crank length, L3 is the coupler length, and L4 is the follower length. Not only that, we can also see that B2D, which I have got as L2, is nothing but L4 sine of theta 4 star by 2, because this angle is theta 4 star by 2. So, there is another relationship for such a linkage without quick return, that the crank length must be follower length into sine theta 4 star, that is the swing angle of the rocker, divided by 2. So, these are the two very important relationships which can be used while designing a mechanism. Let us now look at the model of this Crankrocker linkage without quick return that we have just discussed. This is a Crankrocker linkage where L1 squared plus L2 squared is L3 squared plus L4 squared. This is the one extreme position where the crank and the coupler has fallen in one line. This is one extreme position of the follower. Now, as it rotates to 180 degree, again the crank and the coupler becomes collinear, giving rise to the other extreme position of the follower. As a result, this 4R linkage, if the crank rotates at uniform speed, the forward and return motion of the follower takes equal time and there is no quick return. Now, let us look at the model of this Crankrocker linkage where L1 squared plus L2 squared is not the same as L3 squared plus L4 squared. As a result, the extreme position of the follower that it takes is due to unequal rotation of the crank. One extreme position is here when the crank and the coupler has fallen in one line. Now, from here it rotates through this angle, again the crank and the coupler falls in one line, giving rise to the extreme position of the follower. So, here as we see, the follower does not take equal time during its forward and return motion. So, there is some quick return effect depending on, of course, whether I am rotating clockwise or counterclockwise. Here theta 2 from here to there is more than here to there. So, if I rotate it clockwise, you can see the return is quicker. Let us now look at another model where again it is a Crankrocker linkage, but L1 squared plus L2 squared is much less than L3 squared plus L4 squared. Consequently, the quick return effect will be much more predominant. For example, this is one extreme position and the other extreme position is taken here. So, the angle that the crank rotates is much more than pi and the angle through which it returns is much less than pi. So, if we move the crank at uniform speed, the quick return effect is much more predominant. The follower is taking much longer to come from right to left extreme and much less time to go back. Now that we have discussed both graphical and analytical methods of displacement analysis, let me show you through an example how both these methods can even be combined while designing a particular mechanism. As an example, let us consider this windshield wiper mechanism, which is a 6-link mechanism. This figure shows the mechanism to a particular scale. For example, this distance is 50 millimeter. That is the scale of this diagram. Let us now see this mechanism. This has O2, A, B, O4. This part is a Crankrocker mechanism. and then this link 4 is extended beyond O4, and we have another 4R mechanism, namely O4, C, D and O6. And the second 4R mechanism, that is O4, C, D, O6, is in the form of a parallelogram. O4C is same as length in O6D, and length CD is same as length O6O4. And this wiper blade is an integral part of the coupler of this parallelogram linkage, that is link number 5. The wiper blade is same as link number 5. The first part of the question is, what is the wiping field? That means, as this crank O2A is driven by a motor, what is the field that is wiped by this wiper blade? Now, to solve this problem, what we do, first we use a little bit of graphical method. We study only this 4-bar linkage, namely O2AB04, and determine the extreme positions of this link O4B, that is link number 4. For that, we know, as usual, B is going along a circle with O4B as radius. This is the circle with O4 as center and O4B as radius, that we call the path of B, say KB. The extreme positions of B will be taken up when the links O2A and AB become collinear. So, the furthest point B can go is when the distance of B from O2 is O2A plus AB. So, I take O2 as center and draw a circular arc with L3 plus L2 as radius, and let that intersect KB at this point. This I call B2. And other extreme position of B will be taken up again when AB and O2A will be collinear, and the distance of B from O2 will be equal to L3 minus L2. So, I draw a circular arc with O2 as center and L3 minus L2 as radius, and let that intersect KB at this point B1. So, O4 B2 is one extreme position of link 4, and O4 B1 is the other extreme position of link 4. Now, as we see, the link 4, this extension O4C is not in line with O4B. There is an angle delta which has been prescribed as 16 degree. So, we can draw the extreme positions of, we have already determined B1 and B2 as explained earlier. When corresponding to B2, I draw this line O4C2 at an angle delta, which was 16 degree, and corresponding to B1, again I draw at an angle delta 16 degree to get C1. So, O4C2 and O4C1 are the two extreme positions of the link 4. Now, the question is, as we know, because the second part of the mechanism was a parallelogram, so this line CD always remains horizontal and the wiper blades always remain vertical, because there is no rotation of the coupler of this parallelogram linkage. We have already determined the extreme position C1 and C2, so I can draw the wiper blades as E2, F2, and other extreme positions when C is at C1 as E1, F1. So, these are the two extreme positions E2, F2 and E1, F1 for the wiper blade. To determine the wiping field, we see that because it is a parallelogram linkage, the point C which goes in a circle with O4 as radius and O4C as O4 as center and O4C as radius. Because it is a parallelogram linkage, all the points of the coupler move in identical curves. That means the curve generated by the points E or F, that is the end of the wiper blade, also will be similar circles, exactly of same radius as O4C. Only thing, the center of the circle will be shifted from O4 to CE for the point E, and O4 to CF for the point F. That is, CE-CF is same as E2-F2 and E1-F1. So, with center as CE and radius as O4C, which is same as CE1, I draw this circular arc. Similarly, center as CF, I draw this circular arc, and these are the two extreme positions, and the wiping field is what has been shown by these hatched lines. So, we have obtained the field of wiping for this particular mechanism. Let me repeat. First, we said determine the path of B, which is this circle with O4 as center and O4B as radius. On this circular path, I locate B1 and B2 using the relation O2B1 is AB minus O2A, O2B2 is AB plus O2A. Once I have got the extreme positions of link 4, I draw O4C2 and O4C1 corresponding to O4B2 and O4B1. Because link 4 is a rigid link, the same angle delta is maintained between the line O4B and O4C. Once we get the extreme positions of the point C, I draw the wiper blades which always remain vertical because of the parallelogram linkage as E2F2 and E1F1. Because of the parallelogram linkage, all the coupler points generate same circular arc as O4C. Only thing, the center of the circle is shifted in a symmetric fashion from C2 to E2, that is O4 to CE, C2 to F2, that is O4 to CF. These are all on the same vertical line. As a result, we get the complete field of wiping as generated by this particular wiping mechanism. We demonstrate the same wiper mechanism that we have just now studied. This is the same wiper mechanism consisting of a crankrocker consisting of link 2, link 3 and link 4. O2 and O4 are the two fixed hinges. And there is another parallelogram linkage starting from here, link 4, link 5 and link 6. This link length is same as this link length and this link length is same as this link length. So, it is a parallelogram, and we should note, because it is a parallelogram linkage, the coupler remains always parallel to itself, it never changes its orientation. So, as the motor here rotates, the coupler wiper blade goes from left to right, generating a field of wiping, but the coupler blade always remains vertical. Now that we have obtained this field of wiping for this particular given mechanism, let us observe that this wiping field, that is E1, E2, F2, F1, E1, this field of wiping is not symmetrical about the line, vertical line passing through O4. This O4V is the vertical line passing through O4, but the field of wiping is more on the right and less on the left. So, as a designer, maybe we can make a very little change to make this field of wiping symmetrical about this vertical line. So, the second part of the problem is retaining all other link parameters same, change only the angle delta, which was given as 16 degree, change only this angle delta to make the field of wiping symmetrical about the line O4V. To solve this problem, what we do, we find what is the angle of oscillation of this rocker link O4B, that is from O4B1 to O4B2, that is the theta 4 star, which we call the angle of swing. This theta 4 star is not symmetrical about the vertical line. As a result, the field of wiping is also not symmetrical about the vertical line. This theta 4 star we measure, and then theta 4 star by 2 and theta 4 star by 2 symmetrically about the vertical line through O4. We have already seen that B1, which is the extreme position of the link O4B, which we have obtained earlier, here this B1, that is this B1, and now O4C1 must be like this to make the field of wiping symmetrical, because now I have made O4C1 and O4C2 symmetrically placed about the vertical line just at an angle theta 4 star by 2 and theta 4 star by 2, because theta 4 star is entirely decided by all the link length, that I cannot change. But now this is O4B1 and this is O4C1. So the extension of O4B1 and this line O4C1, the angle is delta. This is the angle delta which should be provided rather than what we had earlier as 16 degree. Now, the third part of the problem, we can have some more specifications. For example, we define what is the width of this wiping field, that is this horizontal distance C1, C2. So let me pose a problem that modify this design, but you are allowed to change only the crank length O2A and this coupler length AB and the angle delta to satisfy three requirements, namely the wiping field should be symmetrical about the vertical line O4B, and the width of the wiping field, that is the horizontal distance between these two extreme positions E1F1 and E2F2, is say 450 millimeter to the same scale, and there should be no quick return. That means O2A1 and O2A2, these two extreme positions corresponding to these extreme positions of the follower, the crank angle should be 180 degree. So we have no quick return, for which we need L1 squared plus L2 squared is same as L3 squared plus L4 squared. Now the width C1, C2, we can easily see it is 2 times O4C into sine of the angle theta 4 star by 2, because this angle is theta 4 star by 2. So this horizontal distance is O4C sine theta 4 star by 2. Twice of that is the width of the field of wiping. This has been specified as 450 millimeter. The length O4C has not been changed, so we had it already given in the design. So substituting that value of O4C, I can find what is the theta 4 star value, and we can find what is theta 4 star. So we determine theta 4 star from this equation with the given value of O4C. Now that we know theta 4 star, if you remember, for no quick return, we also had a relationship that L2 must be L4 sine theta 4 star by 2. Now L4, that was the link O4B, was not allowed to be changed. So now that L4 is given and theta 4 star we have obtained, so I can obtain the crank length O2A as L2. So I have obtained L2. L1 has not been changed, L4 has not been changed, L2 we have obtained. So using this relationship for no quick return, I can get the only remaining unknown, that is L3. So we have designed the 4R linkage O2AB04. To obtain the required value of delta, we just with the new lengths L2, L3, L1, L4 were unchanged, I again obtained what is the path of B, which is this circle. And O2 B1, as we know, was L3 minus L2. So from O2 I draw a circular arc O2 B1 as L3 minus L2. So I get the extreme position O4 B1, and the extreme position O4 C1 is already known. So the angle between the extension of O4 B1 and O4 C1 determines the required value of delta, which as we see is much less than the original value, which was 16 degree. This delta, if you draw it correctly, comes out around 5 degree. So we have modified the design to satisfy three requirements, namely the field of wiping has to be symmetrical, has to be symmetrical about the vertical line O4V, has to be of a particular width, and also there should not be any quick return effects such that the wiper blade takes equal time in the forward motion and return motion. It should not go very fast in one direction and very slowly in the other direction, which will definitely disturb the driver. Now that we have completed our discussion on displacement analysis both by graphical and analytical method, let me start with a very important index of a good mechanism. As we know, the mechanism has to satisfy the geometric requirements, but satisfying the geometric requirement is not all. For a real life mechanism, it must move freely, and this free running quality of a mechanism is quantified by a parameter which is called transmission angle. Let me now discuss this concept of transmission angle and show how to calculate the transmission angle at least for 4 link mechanisms. Let me repeat, for smooth running of a mechanism, one requires that the output member receives a large component of the force or torque from the member driving it along the direction of output movement. This will ensure that the mechanism runs freely. Not only it satisfies the geometric requirements or kinematic requirements, it must have this quality of smooth or free running. However, to ensure this smooth and free running, one needs to have a complete dynamic analysis. That will be discussed much later. However, even at this stage of kinematic design, what we do, we neglect inertia, friction and gravity and treat all the binary links as 2 force members, that is transmitting only axial force. With this assumption, the free running quality of a mechanism can be expressed in terms of what is called transmission angle. Let me explain this concept of transmission angle for a 4R Crankrocker linkage. This diagram shows a Crankrocker linkage, namely O2, A, B, O4, and let O2A be the crank. As we said, if we assume that coupler AB is a 2 force member, then the entire force that AB exerts on the output member O4B is along the line AB. So, this is the direction of the coupler force. However, it is only this component which is perpendicular to the follower produces torque to drive the coupler. So, we have to ensure that this angle is as small as possible. However, for defining the transmission angle, it is defined as the acute angle between the coupler, that is AB, and the follower O4B. This is what is shown as the angle mu. So, we define the transmission angle is equal to mu, which is the acute angle between the coupler and the follower. Obviously, the best possible value of mu is 90 degree. Then the entire coupler force is used to produce torque about O4 to drive the follower. However, as the mechanism moves, this angle mu changes, but one has to ensure that mu does not fall below a particular minimum value, and normally minimum value of mu is prescribed around 30 degree. Next, we will show, because we are only interested in ensuring the minimum value of mu, can we find out for what crank position, that is for what value of theta 2 the minimum transmission angle occurs, because this angle mu keeps on changing with the crank position. It depends on theta 2. It can be easily shown that if it is a Crankrocker linkage without any quick return, that is L1 squared plus L2 squared is L3 squared plus L4 squared, then mu attains its minimum value, that is mu min, when this angle theta 2 is either 0 or pi, that is the crank is along the line of frame O4 O2, that is theta 2 is either 0 and pi. To get this result that mu attains its minimum value for theta 2 equal to 0 and pi, if there is no quick return, that is this L1 squared plus L2 squared is equal to L3 squared plus L4 squared, this relationship holds good. It is very easy to show if we consider the length O4A. O4A I can write in terms of L3, L4 and mu. Considering the triangle O4AB, I can write O4A squared is L4 squared plus L3 squared minus twice L3 L4 cos mu. Same way, I consider again the triangle O4 O2A and write O4A squared as L1 squared plus L2 squared minus twice L1 L2 into cosine of pi minus theta 2, that is plus twice L1 L2 cos theta 2. To obtain an expression for the transmission angle mu, let us consider the triangle O4AB. Then we can write O4A squared is L3 squared plus L4 squared minus twice L3 L4 cosine mu. Same way, if we consider the triangle O4A O2, then I can write again O4A squared is L1 squared plus L2 squared plus twice L1 L2 cosine theta 2. If this Crankrocker linkage has no quick return effect, that means L1 squared plus L2 squared is same as L3 squared plus L4 squared, then I can get an expression for cosine mu as L1 L2 divided by L3 L4 into minus of cosine theta 2. For mu to be maximum, we see that values of theta 2 can be either 0 or pi, because we have to remember if this angle is more than 90 degree, then I will take pi minus this angle between the coupler and the follower as my transmission angle. Transmission angle is defined as the acute angle between the coupler and the follower. Here in this diagram the angle happens to be acute, so it is cos mu. It is mu. But if when this angle becomes obtuse, then I will have to take 180 degree minus this angle as my transmission angle. So transmission angle is minimized when theta 2 is either 0 or pi for this particular situation. That means the crank falls in line with the frame, that is O4 O2. This will show now through models, but if there is quick return effect, then the minimum transmission angle occurs either at theta 2 equal to 0 or at theta 2 equal to pi. Only when there is no quick return effect, then it will be at both locations theta 2 equal to 0 and pi. This figure clearly shows that when the crank O2A is along the line of frame O4 O2, the transmission angle, that is the angle between the coupler and the follower, is at its minimum value. This is what we call mu min, because it is already acute. However, in another situation, we see that the crank O2A is again along the frame line O4 O2, and the angle between the coupler and the follower, that is this angle, is more than 90 degree. So here we will define pi minus mu as my transmission angle. It will always take the acute angle, and this angle is minimized when O2A is along the line of frame. So, there are two situations, either O2A is in this direction when this angle between the coupler and the follower is more than 90 degree and the transmission angle is pi minus mu. The other situation is when O2A is again along the line of frame and the coupler and the follower makes an acute angle, and that itself is the minimum transmission angle mu min. This now we will demonstrate through models. We consider this model of a Crankrocker linkage without any quick return effect, that is L1 squared plus L2 squared is L3 squared plus L4 squared. For such a linkage, as I told you, the minimum transmission angle occurs when the crank is along the line of frame. This angle between the coupler and the follower reaches its minimum value. However, again when the crank falls along the line of frame, this angle is maximized, that is the transmission angle which is defined as the acute angle between the coupler and the follower, that I can see by extension of the coupler and the follower, that angle is minimized. So, the minimum transmission angle occurs at two orientations, two configurations, one is this and the other is this, when the transmission characteristics is very bad, because most of the pull of the coupler is not going to drive the follower. This perpendicular component of this axial force is minimum. Here it is very good. When it is 90 degree, all the coupler force is trying to drag the follower. Here the transmission is very good. Here the transmission is worst, and here the transmission is worst. Now let us look at this another model where L1 squared plus L2 squared is not the same as L3 squared for L4 squared. Here the minimum transmission angle occurs only for this configuration, when the crank and the frame are along the same line and the angle between them is maximized, so the transmission angle is minimum. Here the transmission quality is poor, and here the transmission quality is very good when the angle is close to 90 degree. Let us look at this model again where L1 squared plus L2 squared is not same as L3 squared plus L4 squared. So, here the minimum transmission angle occurs only for this configuration when the crank is along the line of frame and the angle between the follower and the coupler is very small, giving rise to very poor transmission characteristics. However, in this configuration, when again it is crank is along the line of frame, the angle is quite large, and this is not the minimum transmission angle. So, if there is no quick return, then the minimum transmission angle occurs either here or when this angle is 180 degree. But if there is no quick return, then it happens both at this position and at the 180 degree position, as shown earlier. We now explain the concept of transmission angle with reference to a slider crank mechanism. This figure shows a slider crank mechanism where the slider is at B undergoing horizontal translation and O2A is the crank. It is obvious that if the connecting rod AB is horizontal, then the entire connecting rod force is in the direction of movement of the slider. Consequently, we define the transmission angle as mu, that is the angle between the connecting rod and a direction perpendicular to the line of movement. The most desired value of mu is 90 degree, but to ensure smooth free running of the mechanism, mu min, minimum value of mu, should not fall below say around 30 degree. Now, we can find out for what value of the crank angle, that is theta 2, the minimum transmission angle occurs. For that, we see this vertical distance is L2 sin theta 2, which is also same as L3, this is 90 degree minus mu. So, that is L3 cos mu plus E. As theta 2 changes, L3, L2 and E are constant, so mu changes, and minimum value of mu will take place depending on whether E is this way, or suppose the offset was below this line, the direction of sliding is like this, then this distance would have been called E. Depending on whether E is upward or downward, one can easily find that mu min will be cos inverse L2 plus E by L3, and that occurs either at theta 2 equal to pi by 2 or 3 pi by 2, depending on the direction of E. This I leave for the students to decipher themselves, and that will add to the understanding. One can also see this slider crank mechanism at a 4R linkage with O4B, the hinge O4 at infinity. Then you see O2, A, B, O4 is the equivalent 4R linkage, and mu is nothing but the angle between the coupler AB and the follower O4B. So this concept of transmission angle we have used is same for both the 4R linkage, Crankrocker linkage, and this slider crank mechanism. Let me now summarize what we have learned today. We continued with our discussion on displacement analysis of planar mechanisms by analytical method. Then we obtained certain important results so far as 4R Crankrocker linkages are concerned, with reference to its quick return effect and transmission angle, and also where the minimum transmission angle occurs, which has to be ensured for a free running of a design mechanism. And we have also seen through an example that how we can combine both graphical and analytical methods to improve the design or modify an existing design.